ancient times, in a vast and unknown space, a story was born that transcends time itself. In that boundless place, a single force gave rise to everything we know today as our universe. It was a unique moment known as the Big Bang. In an infinitesimal point called Singularity, all matter, energy, and space-time were compressed into an undifferentiated entity. Without time, without space, without a clear direction, this singularity was like a dark spark, waiting to ignite into a cosmic fire. And so it was. In a supreme explosion of energy and light, the singularity erupted, giving birth to our universe. This explosion was not just a physical manifestation, it was the beginning of time, space, and matter, an incredible journey into existence. In the first moments of this process, temperatures and densities were so intense that not even particles of matter could have survived. However, in this hot and dense plasma, wonderful things happened. During these early milliseconds of existence, the conditions were extremely hot and dense, and the universe was completely unknown. However, in that initial chaos, processes and events unfolded that laid the groundwork for everything that was to follow. In just a few fractions of a second, the universe cooled and began to expand rapidly. Within the first moments of this expansion, the universe was a seething sea of subatomic particles, including quarks, gluons, and leptons, interacting in a high-energy plasma state. The temperatures were so intense that even protons and neutrons, the building blocks of atomic nuclei, could not form. However, as the universe continued to expand and cool, approximately 10 to 6 seconds after the Big Bang, the quarks and gluons combined to form protons and neutrons, heralding the beginning of the era of nucleosynthesis. 1 second after the Big Bang, the universe consisted of an extremely hot 18 billion degrees Fahrenheit or 10 billion degrees Celsius, primordial soup of light and particles. In the following minutes, an era called nucleosynthesis, protons and neutrons collided and produced the earliest elements: hydrogen, helium, and traces of lithium and beryllium. After 5 minutes, most of today's helium had formed, and the universe had expanded and cooled enough that further element formation stopped. At this point, though, the universe was still too hot for the atomic nuclei of these elements to catch electrons and form complete atoms. The cosmos was opaque because a vast number of electrons created a sort of fog that scattered light. Around 380,000 years after the Big Bang, the universe had cooled enough that atomic nuclei could capture electrons, a period astronomers call the epoch of recombination. This had two major effects on the cosmos. First, with most electrons now bound into atoms, there were no longer enough free ones to completely scatter light, and the cosmic fog cleared. The universe became transparent, and for the first time, light could freely travel over great distances. Second, the formation of these first atoms produced its own light. This glow, still detectable today, is called the cosmic microwave background. It is the oldest light we can observe in the universe. Scientists used 9 years of data from NASA's Wilkinson Microwave Anisotropy probe to create this detailed all-sky image of the cosmic microwave background. The image reveals 13.8 billion-year-old temperature fluctuations, shown as different colors. seeds that grew into the galaxies we see today. After the cosmic microwave background, the universe again became opaque at shorter wavelengths due to the absorbing effects of all those hydrogen atoms. For the next 200 million years, the universe remained dark. There were no stars to shine. The cosmos at this point consisted of a sea of hydrogen atoms, helium, and trace amounts of heavier elements. Gas was not uniformly distributed throughout the universe. Cooler areas of space were lumpier with denser clouds of gas. As these clumps grew more massive, their gravity attracted additional matter. As they became denser and more compact, the centers of these clumps became hotter. Hot enough eventually that nuclear fusion occurred in their centers. These were the first stars. They were 30 to 300 times more massive than our sun and millions of times brighter. Over several 100 million years, the first stars collected into the first galaxies. The birth of stars heralded a new era in cosmic evolution. Within the cores of these celestial giants, the intense pressure and temperature gave rise to nuclear fusion reactions, converting hydrogen into helium and releasing tremendous amounts of energy in the process. These stellar nurseries became the engines of creation, seeding the cosmos with heavier elements forged in their fiery cores. As stars exhausted their nuclear fuel, they underwent dramatic transformations, culminating in explosive deaths known as supernova explosions. These cataclysmic events scattered newly synthesized elements across the cosmos, enriching the surrounding space with a diverse array of chemical elements. The remnants of these ancient stars, along with the debris from supernova explosions, coalesced over time to form the next generation of stars and planetary systems. Within these stellar nurseries, planets, moons, and asteroids formed from the leftover debris, providing fertile ground for the emergence of life. Over billions of years, Galaxies took shape, each containing billions or even trillions of stars bound together by gravity. These vast cosmic cities became the building blocks of the universe, shaping its structure and influencing its evolution on a grand scale. Thus, from the fiery crucible of the early universe to the majestic tapestry of galaxies and stars we observe today, the cosmos has undergone a remarkable journey of transformation and evolution. Each stage in this cosmic saga has played a crucial role in shaping the universe as we know it, from its humble beginnings to its awe-inspiring complexity. Eventually, in a remote corner of the universe, an ordinary star ignited, and around it formed a small solar system, which includes a small and insignificant planet called Earth. As the newly formed Earth cooled, its surface underwent profound changes. Volcanic activity spewed forth gases and minerals, creating a primordial atmosphere and oceans. Within these ancient seas, the stage was set for the emergence of life. The exact mechanisms by which life arose on Earth remain shrouded in mystery, but scientists speculate that early Earth provided the ideal conditions for the formation of organic molecules, the building blocks of life. In the warm, nutrient-rich waters of the ancient oceans, simple organic compounds began to interact and combine, giving rise to increasingly complex molecules. Over millions of years, these organic molecules underwent further chemical reactions, eventually forming the first self-replicating entities. These primitive life forms, likely resembling simple bacteria or archaea, thrived in the ancient oceans, harnessing energy from sunlight or chemical sources to sustain themselves. Through processes of mutation, competition, and natural selection, life on Earth diversified and evolved into myriad forms, adapting to a wide range of environments and ecological niches. Over billions of years, simple cells gave rise to more complex organisms, including multicellular life forms such as plants, animals, and fungi. The history of life on Earth is marked by significant milestones, including the colonization of land by plants and animals, the emergence of complex ecosystems, and mass extinction events that reshaped the course of evolution. Despite these upheavals, life on Earth persisted and thrived, demonstrating remarkable resilience and adaptability. The emergence of intelligent life forms such as humans represents a relatively recent development in Earth's history. With their advanced cognitive abilities and capacity for innovation, humans have reshaped the planet in profound ways, altering landscapes, ecosystems, and even the composition of the atmosphere. From its humble beginnings in the ancient oceans to the present day, life on Earth has undergone a remarkable journey of evolution and adaptation. Each species that has ever existed on this planet is part of an intricate web of life, interconnected and interdependent in ways that continue to shape the biosphere. As we strive to understand the origins and evolution of life on Earth, we gain insights into our own place in the cosmos and our responsibility to steward the planet for future generations. The future of the universe is a topic that encompasses a wide range of scientific theories and hypotheses, each offering insights into the potential fate of the cosmos. While our understanding of the universe's ultimate destiny is still evolving, several key possibilities have been proposed based on current observations and theoretical models. One prominent theory is the idea of the Big Freeze or heat death of the universe, which suggests that the universe will continue to expand indefinitely, leading to a state of maximum entropy where energy is evenly distributed and all thermodynamic processes cease. In this scenario, stars will eventually burn out, galaxies will drift apart, and the universe will become a cold, dark, and desolate expanse. Another possibility is the Big Crunch, where the universe's expansion eventually slows and reverses due to the gravitational pull of matter, leading to a collapse back into a singularity similar to the Big Bang. This cyclic model suggests that the universe undergoes an infinite series of expansions and contractions, with each cycle beginning anew. Alternatively, some theories propose that the universe could undergo a Big Rip, where the expansion accelerates to such an extent that it tears apart galaxies, stars, and even atoms, resulting in the complete dissolution of matter and the fabric of space-time. It's important to note that our current understanding of the universe's fate is limited by the constraints of our scientific knowledge and observational capabilities. As our understanding of fundamental physics and cosmology advances, new theories and insights may emerge, reshaping our understanding of the universe's ultimate destiny. In summary, the future of the universe remains uncertain, with various possibilities ranging from eternal expansion to eventual collapse or dissolution. Continued scientific exploration and observation will be crucial in unraveling the mysteries of the cosmos and understanding its ultimate fate. While the future of the universe holds many uncertainties, it also presents an opportunity for further exploration and discovery. As we continue to unravel the mysteries of the cosmos through scientific inquiry and observation, we inch closer to understanding the ultimate fate of our vast and awe-inspiring universe.